Here we have an example. A police car's siren emits a sinusoidal wave with frequency 300 Hz. The speed of sound is 340 meters per second and the air is still. Letter A, find the wavelength of the waves if the siren is at rest. Letter B, find the wavelengths of the waves in front of and behind the siren if it is moving at 30 meters per second. First we draw the problem. The first case, the siren is at rest. We see that the wave front has a symmetrical shape and we expect that the wavelength is the same at all sides. The second case, find the wave front appears deformed as it moves at a speed. We expect that the wavelength is different at the front and at the back. So for a speed of a source at rest, the sound radiates symmetrically with a speed of sound equal to 340 meters per second. Recall the equation of wavelength, which can be expressed as the speed of sound over the frequency of the source. The calculation shows that the wavelength is equal to about 1.13 meters for a source at rest. For a source moving at a speed 30 meters per second, we see that the wavelength is different at the front and at the back. We recall the expression for the wavelengths for the front and at the back. For the front, we see that the length is shorter due to the same direction of the source and the wave front. Substituting the values, we get that it is about 1.03 meters. Now at the back, we see that the wavelength is expanded due to the opposite direction of the wave front and the source. We get that it is about 1.23 meters at the back of a moving source.